Thank you everybody for coming, for joining to this new session of the ILCLI seminar. As you know, we have with us today Bruno Jacinto from the University of Lisbon and Blanco also.
Yes.
Well, the title of the talk, Ordinals and Logicism. So, whenever you want, go on please.
Thank you, and thank you so much for inviting me. It has been a pleasure so far being in Indonesia, my first time, and it's just amazing. Before I start, I just want to say that don't be scared by the handout. The handout has details that are not appearing in the slides. It's just for the aficionados. So for those that would like to check in more detail what's going on. I'll try to give the rough ideas. I'll be a bit more technical in some places, but not as in the handout. Okay, so the aims for today. The first aim is to formulate a higher type resolution of the Burali-Forti paradox. To anticipate, we'll start by looking at the Burali-Forti paradox. I think it's a real paradox, not one that's solved by set theory. And then I'll try to show how I think one should proceed to solve it in broad strokes. And then I'll present a metaphysical problem for broadly abstractionist conceptions of ordinals. And this will turn out to be important because there is a competing view on ordinals or on ordinal talk that has been recently proposed, as you'll see later on. And I'll try to show that that view faces a metaphysical problem that has been known for a bit. And then I'll show that my own characterization of ordinals does not suffer from that problem, so it fares better. And then perhaps its most direct competitor now in the literature. And I'll show that it delivers, in a particular sense, a robust theory of ordinals. A particular sense I'll make precise later on. And this particular sense, in which it is a robust theory, if you want to say a strong theory, is one that lends support to a theory I've been defending in the past. So in the past, I've defended what I've called upper logicism about arithmetic. You'll come to see what that is later on. But I think that the results I have support a form of logicism also about ordinals. To anticipate, I know that you've been having some talks on Frege. I mean, we are all, in a sense, descendants of Frege in philosophy of mathematics, in philosophy of language. But the best way to approach the kind of logicism that I'm proposing, and that I'll be proposing, is actually not Frege's, but Russell's. So that, I think, will be important later on. So if you have Frege in mind, reset that, think about Russell and how Russell, and this type theory and how we try to recover arithmetic. Okay, so let's start by reviewing briefly the Burali-Forti paradox. It can be deployed in second-order logic without using any set theory. That, I think, is quite important. We need full comprehension. That just tells you basically that any formula defines a property or a relation if it has two variables, or a binary relation or ternary relation if it has three. That's full comprehension. That's all that you need to know about that principle. Okay, and then in particular, this formula can have quantifiers in it, quantifiers over relations and properties and so on. So the paradox relies, besides second-order logic, just on this principle, ordinal abstraction. It says that for any two orderings, their ordinal is the same, just in case they're order isomorphic. And to be order isomorphic is just to say that if I have a ordering, so I have objects following one next to each other, say that they are order isomorphic is just to say that there is a bijection between the two orderings that preserves the order. Nothing more than that. So if we have this kind of bijection, then the ordinal, so let's suppose these are two relations, R and S. So we get that R and S, are isomorphic, order isomorphic. Yes? Sorry? It's a function that, I mean, it's functional, but it stands for a function that maps relations to objects, binary relations. That's, of course, and that turns out to be crucial for the paradox. So it's a function from relations to individuals. And yeah, I think this is all that's needed to present the paradox. WO says that R and S, R and WS says that they are well orderings in the sense I've just explained. Or I mean, well ordering, you can just think that it's a sequence of stuff such that any non-empty set has at least an element. But some of these details are actually in the handout. So for the curious, you can check them. Say that an individual is an ordinal, just in case it is the ordinal of some ordering. That's a very natural way of throwing out the notion of ordinal, given that we have ordinal abstraction. Then, and given ordinal abstraction, you can define a relationship of less than relation between a relation of less than between ordinals, in terms of relations between well orderings. So the relation between well orderings is the following: R is smaller than or equal to S, just in case R is isomorphic either to S or to an initial segment of S. And then you can say that the ordinal of R is smaller than or equal to the ordinal of S, just in case the relations of which they are ordinal, then ordinals stand in this less than relation. So it is provable then that this relation on the ordinals is well ordering. And so, since this relation, any relation is some order isomorphic to itself, it follows from ordinal abstraction that there's such a thing as its ordinal. I mean, this would already follow in a non-free logic, but even assuming that the logic is free. So there is some ordinal O, which is the ordinal of the well ordering of the ordinals. By ordinal abstraction, we also get that any well ordering with ordinal O is isomorphic to the restriction of this relation. So this restriction is the restriction of the well ordering of the ordinals to those which are less than O. So we get that a relation, a well ordering, is isomorphic to a restriction of the well ordering. But by second order logic, this is impossible. So that gives us the paradox. So what we need to know is that we cannot get this result. We cannot get that well ordering is isomorphic to a restriction of it to one of the things it relates. So that's what makes the argument work, the paradox go through. Okay, so I'll just lay down the bare bones, so the structure for a higher type resolution of the paradox, which is not the full resolution, that will come later in the talk. But a natural view on the ordinals is that they are properties of well orderings. So the typical talk, even for mathematicians, is that ordinals are well ordering types. If you're doing set theory, so if some of you are used to treatments of ordinals in set theory, then we equate the ordinals to particular sets, which are supposed to be representatives of these types. But there's not representatives in particular, precisely because we can make these isomorphisms between these ordinals you're using. You use the term yardstick and any other thing which would be of the same type. But really, it would appear that ordinals should be types, should be properties of well orderings. So the resolution is just take that kind of talk seriously. But if you take that kind of talk seriously and you use higher order logic and higher order quantification, then you obtain the following view. Ordinals are properties of well orderings. That is roughly for any, or let's stick for individuals. Then if you have a relation between individuals, which I'll denote like this, a binary relation between individuals, the ordinal is a property of a relation. So it's of this type. So just to make clear what the notation I'm using the following. E stands for the type of individuals, and if I have types tau1 to tau n, standing for entities of types tau1 to tau n, then I can talk about the relation between entities of that type, and that relation will be of this type. So in particular, if I have a property of individuals is a unary relation if you want. So I represent it like this. Property of individuals, I represent it like this. And if I have a relation between individuals and the property of individuals, I represent it like this. And so here, this is, an ordinal is a property of ordinals. A property of relations between individuals, of well-orderings in particular. So the ordinal of well-ordering is of a type higher than the type of the well-ordering. That's what you can see. Whenever you have further brackets, the type is higher. That's like the good rule of thumb. Hence, it makes no sense to speak of the restriction of well-ordering to its ordinal. For it is nonsensical to say that the property of well-ordering is related by that well-ordering. So well-orders represent, if a well-ordering relates individuals, it won't relate properties between individuals. That violates type restrictions. In particular, it would be nonsense. And that's what I'm saying here. Ordinal abstraction is then regarded as nonsensical. It presupposes that the ordinal of a relation is of the same type as relations relata. Coming back to the question on the functional ord, it's mapping relations to individuals where it should be mapping relations to properties of individuals. We'll consider further lessons from the Burali-Forti paradox later on. But this was what I wanted to put on the table. So the bare bones of the resolution. So in getting to the important topic of this talk, so what are the ordinals then? Higher type ordinals, the principle I've presented to you, should look as insufficient as a characterization of ordinals. So call it higher type ordinals, just says that they are properties of well-orderings. That gives us nothing about what their nature is. It should be important to get clear on what the ordinal is, because it would appear that our best hold on ordinals comes from ordinal abstraction. So that if we don't have a good hold on what ordinals is, or what ordinals are, then it might be that we're kind of equivocating on what we mean by ordinal, and that at the end of the day, that notion is best left out of the table. The set theorists can talk about set ordinals if you want, but they're talking about something else. It's not to say that set theorists should revise their practice, it's just that they're not talking about ordinals. They're talking about particular sets. And minimal a higher type characterization of ordinals to make it possible to capture the spirit, if not the letter of ordinal abstraction. So we should have this principle come out true. Two well-orderings fall under the same ordinal, ordinals are conceived as properties of relations, if and only if they are isomorphic. So, and to anticipate, for some this might look as a definition of what it is to be an ordinal, in particular for those that might be looking at it via Phrygian lenses, in the same way that you might think that two natural numbers are the same, just in case they are, the number of f is identical to the number of g if and only if f and g are equinumerous. So if you know about the Neo-Phrygian approach in the philosophy of mathematics, Neo-Phrygians take this principle, Jung's principle, to give you a definition of number. But this is not how I'm thinking about higher type abstraction, because Neo-Phrygians themselves have a problem when they think of principles of this sort, which are called abstraction principles, as giving you definitions of numbers. So this is just a constraint, if you want, on any account to be given of what an ordinal is. And it makes sense, as we see. Two well-orderings, if they fall under these should fall under the same ordinal, and they should fall under the same ordinal precisely because they are isomorphic. Okay, so I've laid down a sketch of my view on the table. Now I want to look at a problem for Neo-Phrygian abstractionists. And I can start then by going again into what Neo-Phrygian abstractionist is. And the crucial notion is that of an abstraction principle. So the idea is that if you have some relation, equivalence relation, FG, if and only if, I'll call it the abstract of F equals to the abstract of G. So a Neo-Phrygian is someone that adheres to principles of this form. In particular, the Neo-Phrygians we know think of the abstraction operator as the number of, and they adhere to the view that the number of F is identical to the number of G if only if the F's are F is equinomorphous with G. So in the first instance, this problem that I'll raise, and it's been published by Donaldson recently, a version of it, but it's kind of been in the, there's been an awareness of it for way longer, is based on the following idea, that the identity and the existence of types is grounded on the obtaining of equivalence relations between tokens. So for instance, think of a number as being as typing a property. 0 types the properties that have no instances, 1 types the properties that have exactly 1 instance, and so on and so forth. So the problem that I'll raise arises for those that think that the existence of 0 is grounded on the equinumerous relation, for instance, that exists between the properties that have no instances. Whenever we have this relation of equinumerosity, lo and behold, you have existence of identity between numbers. So types are grounded on concreta. And there are many ways of being an abstractionist and of adhering to grounded abstracts. You can think that the identity existence of word types of particular inscriptions is grounded on the obtaining of the same shape relation between those inscriptions. And the existence of numbers of properties is grounded on the obtaining of the equinumerosity relation between those properties. And for ordinals, the identity and the existence of the ordinals of particular row orderings is grounded on the obtaining of the isomorphism relation between those row orderings. Just to say, of course, that one thing which is clear is that the abstractionist program, and it's, again, been known for quite a while, doesn't work for ordinals. That's just a direct result of the Burali-Forti paradox. So, or the Neo-Phrygian program, I should say. The metaphysical problem arises from the following theses. The first is serious actualism. The idea is super simple. I find it to be extremely compelling. If things are related, then they exist. That's just what the theses say. And if some of you, I mean, there's actually been some debate on questions having to do with higher order logic and metaphysics on whether serious actualism holds or not. I mean, that I've defended in print, so I will discharge the duty to defend that here. If you're curious, you can check that. But here's one example. These inferences also seem supernatural. If Agnes is a student, Agnes is identical to something. If Sue is a friend of Mike, then Sue and Mike, each one of them is identical to something. Okay, now let me give you the problem for anyone that adheres to grounded abstracts. The problem can be seen, one way of presenting it is via what I've called the knife scenario. Suppose each knife's handle and blade is essential to it being the knife it is. So in the same way that with pens, perhaps it doesn't work as well, but you might think that the pen and I'm lacking the word for the cap, sorry. The pen and the cap, they're like, if you change a cap, then it's not the same pen. If you change what you'd call the actual pen, then it's not the same pen. So at rule W1, there are handle H, weight B star, and knife H plus B. At rule W2, exactly the same world, but what you have is H composing with B star, with weight B star and not B. So what you get is there are only these 4 things. At each row, there are only 4 things, and they are these. An important point to note is that the knife you get when you get handle H with weight B, and the knife you get when you get weight H with B star, they are incompossible. They won't ever exist together because, I mean, for one to exist, you need to destroy the other. Now consider the following, orderings. I've just presented them like that, but H comes first, B comes second, B star comes first, H plus B comes last. Third, and H plus B comes last. So these are relations, so they'll have a modal profile. They'll, at each row, relate different objects. And so you have these 2 L orderings. You know, the metaphysical problem arises from the following. Intuitively, the ordinal of R at W1 is the same as the ordinal of S at W2. So, I mean, just looking at the extension, they should have the same ordinal. But there is no isomorphism at W1 or W2 between R as it is at W1 and S as it is at W2. If there were such an isomorphism, it would relate knives H plus and H plus star, H plus B and H plus B star. So an isomorphism is a relation, it's a function, it's a relation, relates objects, but for the relation to relate H to map, so you can like, if I had a relation that mapped H plus B to H plus B star, it would be relating these two, so they would have to exist. They would have to exist at some world, but there's no world where they can exist together. They're incompossible. So what's the idea, I think, that underlies a metaphysical problem? Is that abstract types allow us to perform cross-world comparisons between tokens in ways that concrete equivalence relations between tokens do not. So let's look again. I can say that they have the same ordinal, and by saying that they have the same ordinal, I can do what I cannot do by relating S at W2 with R at W1. I can say that the ordinal of R at this possibility is the same as the ordinal of S at this possibility. So types allow us to perform these cross-world comparisons that I think concrete relations between tokens do not allow us to do. So the type's existence and identity cannot be grounded on concrete equivalence relations between their tokens. Types are actually required for us to be able to assess whether things fall under the same type when such equivalence relations do not arise, cannot be performed, just cannot hold. So having presented this problem for whoever adheres to grounded abstracts, I'll present you the no-class theory. And I'll show that the same kind of problem arises for it. And the no-class theory is an alternative theory of ordinals. So here it is. It has been proposed recently by Salvatore Florio and Graham Leach-Krauss. And the idea just takes a nod from Russell's no-class theory. The idea then is that statements prima facie about ordinals are really, when you do the Russellian move of like analyzing the logical form, statements about isomorphisms between well orderings of which they are ordinals. And to make this idea more transparent, to make it clear, Florio and Leach-Krauss specify a translation which gives you the real content of statements that would be prima facie about ordinals. And they always proceed in the same way. So when you, for instance, have an identity between the ordinal of R and the ordinal of S, that's really about the relation between S and R. And the way they do it is that really states that there are two well-orderings such that R is isomorphic to the first one, S is isomorphic to the second one, and the first and the second one, T and Q, are actually themselves isomorphic. And you get the same one, you have the same move if you have, instead of the ordinal of R, you have a no. And you translate the connectives compositionally. When you talk about the existence of a relation, again, you do it compositionally. And when you seem to be quantifying over ordinals, that's what the small o stands for, variable over ordinals, really you're quantifying over well orderings. So what's the no-class theory diagnosis of the Burali-Forti paradox? So the idea is that a statement that would appear to state that the ordinal of R stands in the less than relation between the ordinal of S, it's really a statement about well orderings being there being well orderings isomorphic to respectively R and S, which stand in the less than relation. So it's really all statements about well orderings, never statements about ordinals. So statements that involve the relation between ordinals are not really, once the logical form is analyzed, statements about ordinals. They're statements about well-orderings and how they relate. But that means that this function that maps a well-ordering, the supposed well-ordering of the ordinals to an object, to an individual, is not well-formed. Because remember, really when you analyze statements involving this relation, this is not the relation between ordinals. It's the relation between well-orderings. And this function applies only to relations between individuals. It does not apply to relations between individuals, to relations between individuals. So one thing is for this relation to apply to an individual A and B, good, but it does not apply, or it does not apply to relations of this form. Or let me put it that way, to get the ordinal of a relation, I can only get, let me do it like that, and let me use TRS. I can get the ordinal of R because R is a relation between individuals. I cannot get, and so this is well formed, the function that maps T to an individual is not well formed because R and S are relations between individuals. And so T is a relation between individuals. It is of the wrong type. So this yes, this no. So robustness. So they take a theory of ordinals, they say the theory is robust if it derives two principles which are taken to be characteristic of ordinals. Or at least if it derives, on their view, this must derive their translation. The first we've already seen, ordinal abstraction. So the idea is that a robust theory should be able to derive some form of ordinal abstraction. The second one is transfinite induction. That just tells you that if all things that stand, if all the ordinals less than a given ordinal have some property, then the ordinal next to it has that property. If that holds in general, then that holds for all ordinals whatsoever. And they show that in this sense, the null-class theory is robust because they can derive the translations of these principles as theorems of third-order logic. So that's a neat result. Like without talking about ordinals, really, we can get results that would seemingly characterize the ordinals. And this has led them to regard the null-class theory as a logistic theory of ordinals, and that's the other reason why I'm so interested on discussing their view, because they're a direct competitor. Still, I mean, even though the theory they present is robust in their sense, I just want to point out that they cannot derive on their theory the translation of there are more than two ordinals to begin with. So it's not, I mean, you get some theory of ordinals, but it's like, it's not robust. I mean, I don't know if I get as much, a robust theory, but as you'll see, I get more than that. For sure, I don't know what the limits are in my case. Okay, so let me raise then the metaphysical problem for their null-class theory. So it would appear that there's only one way for them to understand modalized statements. It's just to translate them. So if I have a possibly phi sentence, I should translate it possibly and then translate the phi. It's very difficult to see any other strategy to go about. But now consider once more the knife scenario. And now I want you to consider these two well-orderings. R we've already seen, and now we have this second well-ordering U, which at W1 relates H to B, and at W2 is just H. So I'm taking here ordinals to be, or well-orderings to be in a sense of non-strict well-ordering, so that it can relate an object itself. Just because sometimes that's not the way these are defined. We're thinking about strict well-orderings. So presumably, this sentence should be false in the scenario. So that there is an ordinal such that it is possible that ordinal is the ordinal of R, and it's possible that ordinal is the ordinal of U. Just look at R and U. There's never a sense in which you can see, oh, look, this should be the same ordinal as this, or this should be the same ordinal as this, or as this. That never happens. But now, once you translate the statement, it says essentially the following. There is a well-ordering, such that it's possible that well-ordering is isomorphic to R, and that well-ordering is isomorphic to S. And it's possible that well-ordering is isomorphic to S. So again, so it says that there is some well-ordering that such that it is possible that it's isomorphic to R, and it's possible it's isomorphic to S. There are further quantifiers here, but essentially we're always talking about O. Now let O be the following relation. It's a well-ordering, and it matches with R at W1, and matches with O at W2. So then this is a well-ordering which is isomorphic with R at W1 and a well-ordering isomorphic with S at W2. So this shows that this translation yields an incorrect rendering of some statements about ordinals, because they should not fall under the same ordinal ever. These were R and U, sorry. So the translation does not support the claim that statements from a fast tree about ordinals are really statements about isomorphisms. On the contrary, I think that if you look, and once you have modality put into place, you're seeing that the same problem is arising as it was arising before. So the idea is that the null-class series of a kind with theories advocated grounded abstracts. According to it, facts about the ordinal's identity and existence are really just about obtaining isomorphisms between well-orderings. But the lesson we should have gotten already is that that's not so. Ordinals encapsulate more information. Types give you more information than concrete relations between tokens. Okay, so there's a strategy that you might think helps, and that actually connects Javier and me. We're talking about strongly rigid properties in one. So you might think that what you need is to appeal to a particular kind of relations which are strongly rigid. What is a strongly rigid relation? It's so simple, don't look at that, it just says that if it's a relation that if it holds of some objects, it necessarily does. And so if it doesn't, it won't ever. So the no-class theory might be tempted to overcome the metaphysical problem by requiring that statements about ordinals be fleshed out in terms of isomorphisms between strongly rigid well-orderings. Why? What's the idea? Is that these can be seen as yardsticks with which to measure well-orderings. And let me give you some insight into this. So I don't remember the exact details, but suppose that you have here H, B, H plus B. So these are extremely close.
Can you use the black?
Yes, which is here. H, B, H plus B. And so I want to know whether this relation is isomorphic to this one. And this is R at W1. You might think that this is S at W2. Or I want to know whether they fall under the same ordinal, H plus B star. Intuitively they do, but the thing is that I cannot relate this to this object, right? They're never in the same world. They're incompossible. The trick would be, perhaps I can say that they fall under the same ordinal, just in case there is a strongly rigid relation that they are equivalent with. If I can find objects with, I don't know, angel 1, angel 2, angel 3, angel 1, angel 2, angel 3. I'm thinking that angels necessarily exist. For some reason, that's why I'm using angels. Then now I have this angelic ordering that always relates A1 to A2 and A3 in this way. Let's This is angelic, this is A at W1, and it always have the same extension at any world. So this is A at W2, exactly the same well ordering. So if I can find relations of this sort, which are strongly rigid, I can use them as yardsticks and say, oh, look, these fall under the same ordinal because there's an isomorphism between this one in this world, and there's an isomorphism between this one in this world, and they are strongly rigid, and so I can I know that they will have they work as yardsticks in this sense. They tell me that they must have the same ordinal because they never change their profile. And that's basically what this says. I won't go through the details, but the problem, and as you can already see from the knife scenario, is that there is no guarantee that there are these strongly rigid relations for any well ordering. In the scenario I gave you, we didn't have these necessary objects that I could put in these relations. And remember, this solution is not presupposing anything about mathematics or abstract objects, right? It's supposed to just be using logic to give you a theory of ordinals. Okay, so that's so much for and which causes theory. So I'll get you to my view and to my approach. So the crudest way of characterizing ordinals as higher type entities, I think, is the following. So to be an ordinal is just to be such that there is some well ordering, such that the ordinal is a property of being order isomorphic to that well ordering. That won't work for exactly the reasons that I've already shown you before. Because the orderings can change their profile from world to world. They need not be strongly rigid. If I were to strongly rigidify this approach, if I were to say that this relation must be strongly rigid and well ordering, then I would get the same problems that we have here. There might not be such relations. So this is just to say that crude ordinals, which is a simple way of going about this problem, won't work, and that the simple tweak with strongly rigid relations also won't work. So let me cut a long story short. Here's my proposal. And so one thing I like about my proposal, and that most people probably dislike, I like it because mathematically it works, first, and also because it really, I think, captures the idea that types are independent of tokens. Is that the characterization I'll give you of ordinals is highly impredicative. So what I mean by this, it's impredicative in the sense that it is quantifying over entities of the kind that I'm defining. And I'll see what the idea, we'll see what the idea is. Order relations with entities of the kind of ordinals understood as properties of well orderings can be used to establish whether some well orderings of individuals fall under those ordinals. In particular, so let me now so we have the type of individuals, and then I have the type of relations between those individuals, and I have relations between. Yes. Different color. It's a different color. And black. Black is the best. Yeah. So okay. Individuals, then relations between individuals. Then I have the ordinals, which are properties of relations between individuals, and I have relations between the ordinals. Which will be of this type. So here's the idea. If I can find relations between ordinals, or things of the same type as ordinals, which are strongly rigid, I can perform isomorphisms between these relations and relations that are placed here. So let's call S. And I can use these relations between things of the type of the ordinals, these strongly rigid relations, to define what it is to be an ordinal, is to be order isomorphic to any one of these relations. So that's the basic idea. So for this to work, I need to be sure that I have enough relations which are strongly rigid at this level in the hierarchy. I'll make things a bit clearer, perhaps, hopefully, with the definitions. But so the idea then is that these relations, because they will be strongly rigid, they can act as yardsticks with which I can measure whether this is intuitively what the ordinal of this thing is, with which I can measure it. If you think, I think the image of the ruler is really the picture to have. So I can use this as a ruler to see, right, this relation between individuals actually matches with the ruler I have. And so that must be, its ordinal must be different from the ordinal of a different relation if it doesn't match with this ruler, which lives here. So the ruler, again, is a relation that obtains between things of the type of ordinals. In particular, one of those relations will be the less than relation on the ordinals. Though, for my definition, I'm not assuming that this is a relation, that this is the relation on which I'm defining it, that I'm using to define the ordinals. But it's impredicative precisely in this sense, because this is a relation between things of the type of the ordinals, and I'm using these relations which relate things of the type of ordinals to characterize the ordinals. That's basically the idea. So if suppose you have the ordinal 0, 1, 2, 3, then I can use the relational lesson between the ordinal 0, 1, 2, 3 to say whether this relation and this relation fall under the same ordinal. So again, what I need is that I have sufficiently, that the number of these relations here higher in the hierarchy is enough to serve as rulers with which to measure any relation between individuals. So I call these particular relations yardsticks. And the idea is that yardsticks need to be strongly rigid. They need to necessarily exist. I will later say later on that actually the second conjunct, given if I strengthen the logic a bit, is not required. And they need to be such that it is possible that there is some relation here, which is isomorphic to a yardstick. So for R to be a yardstick, there must be some relation at this level, which is isomorphic to that thing. And they must be strongly rigid, so they never change their profile. And this relation must be well ordering. Yes, so if there's a logic I've given you in the handout, doesn't have plural quantification. If I extend that to plural quantification, I can dismiss the assumption that these yardsticks exist necessarily. So I can give an even simpler definition. So what it is to be an upper ordinal, it's just for a property is an ordinal, just in case there is some yardstick such that the property in question is a property of being order isomorphic to that yardstick. So if you want to say theoretically, take any S, T, and suppose these are like all order isomorphic. So you can think of this yardstick, the property of being order isomorphic to this yardstick is a property that holds of S and T and any other things which are isomorphic to it at any worlds at which they are order isomorphic. And then the idea then is look for an entity to be an ordinal, just is for there to be some, just is for it to be an upper ordinal in the way that I've defined, so just is for it to be the property being isomorphic to one of these yardsticks. Having said all this, I need to say something that has been in the background. This view assumes that talk of ordinals is type ambiguous, that I can have ordinals that are properties of relations between individuals, but I can also have ordinals that are properties of relations between relations between individuals, so that I can go higher in the hierarchy. I'll now find ordinals of different types. That's of a piece with the view I'm defending, and that's one place that you might want to get off the boat. But bear in mind that we already have quantification being type ambiguous if you think that higher order languages make sense, so that when you mean what you mean by sum changes according to the type involved. And these phenomena recur. And if I think that ordinals are logical entities to anticipate, they should present the same kind of behavior that things like quantification, the quantifiers do. And so it better be that they are type ambiguous in a way. Something else that I want to say is that I'm not claiming that this gives you the nature of ordinals. In particular, my definition is highly impredicative. What I wanted was a necessary biconditional telling me when something is an ordinal. I wanted to be able to characterize it. And I was in the business of characterizing it using only logical expressions because those we understand. Hopefully. I'm not claiming that there's any other way of going about what it is an ordinal. It's just that we needed some way of fleshing out the idea that made sense, that make it workable. Okay, so we see now that the metaphysical problem won't arise because I'm using yardsticks, and so they have the same modal profile from world to world. I won't go through this. Hopefully it's clear that by using yardsticks, I can use the same relation to measure relations that have different profile, the same profile at different worlds, even if the objects. Again, so H plus B, H, B star, H plus B star. So they should fall under the same ordinal, and I can ensure it if I have enough yardsticks, because I can say that this is order isomorphic to this yardstick, and this is order isomorphic to the same yardstick. And so they must fall under the same ordinal, given the definition of ordinals I've given. Still, as I said, there is some result needed to say, I still need to show that we have enough yardsticks. If I can prove that there are enough yardsticks so that any relation between orderings, so that any ordering falls under some ordinal, then we'll have established higher type ordinal abstraction. And I hope you trust me. The left to right direction of higher type ordinal abstraction, given the definitions, is obvious. But I don't expect you to go through the mathematics there. Just want you to note that this holds. Okay, so that's the game now. I want to be able to derive as a minimal condition to show that my account of ordinals makes sense, higher type ordinal abstraction. And so I'll assume, as a background theory, a pure free type theoretic modal logic. I won't go through the details. If for the curious, so there's a paper where I presented this, but I've also put it in the handout. I will use the theory I have, but I'll add to it two principles. One of them is what I've called finitary plenitude, that says that every finite cardinality could have been instantiated. This is a principle which is quite important to me, so I'll just say something about it. Finite cardinality, if you want, is a quantifier of form. There are exactly n f's, exactly n. And the notion of finite cardinality can be defined using only logical means. And so what this principle says is that the world, and now using a possible world's picture, is such that the world can have any finite number of objects. Perhaps it has infinitely many objects. Actually, I'll say this, but I'll track back. So that there can be a world with 0 objects, there can be a world with 1 object, with 2 objects. I never committed, but this principle does not commit me to the world having infinitely many objects. Sorry. As I said, what I said previously was not strictly true. What I need is that at each world, there is, or that it is possible that there is some world that has a property that has no objects, such that the property has no objects falling under it. There is a world that has some property that has exactly 1 object falling under it, and so on. There can be huge jumps, right? It can be that I have a world with 0 objects and a world with 5 objects, and then I continue. But this is all consistent with there being only finitely many objects. Actually, it's consistent with it being necessary that there are finitely many objects. That's something I wanted to point out to show that, I mean, this principle actually looks quite tame. So if you think that for any finite number there could have been many donkeys, that already suffices to make that principle true. And I'll need a strong assumption about the identity of relations. That if relations are necessarily coextensive, they are the same. That I would like to get rid of. So far, I don't know how to do it. So I'll need a strong form of identity for relations. Necessary coextensiveness suffices for identity. Okay. So this system has these 2 distinctive commitments. Then it's just basically free logic. And what's good about that is that it is consistent with the thesis that has been discussed at least in some spheres, the thesis of contingentism at all orders, which says that for any type whatsoever, there could have been things of that type which could have been nothing. So the existence could have been radically contingent in this way. And what's nice about this is that there are comprehension principles that allow you to derive the existence of properties and relations, which are necessitist, that allow you to derive that whatever relations there are, they exist necessarily. But this is a principle, and I won't go through the details, but this is a comprehension principle that allows you to remain neutral on the debate between contingentists and necessitists. And contingentists, by and large, I mean, I don't know of any contingentist in print that rejects it. I only know of those that accept it. So roughly what it says then is the following. Suppose, I'll use an open formula, but strictly speaking, I should use something else. So suppose I have an open formula, and that formula has parameters, so terms A, B, C, might have some variables, X, Y, Z. So this formula defines a ternary relation just in case the A's, B, and C all exist. So the idea is that I only get the existence of a relation if the thing in terms of which it is defined, they all exist. It is contingent because, think of a property like the property of being Bruno. Some people think that that property only exists when I exist, and that's what I get from this principle. So the property of being Bruno will only exist if the things corresponding to the name Bruno, namely me, exist. Okay, so what we get? We can define the ordering of the ordinals in the natural way, given the definitions I've given you of ordinals by defining it in terms of a relation of less than or equal to between well orderings. And a theorem that I get is that the well ordering of the ordinals is a well ordering, and it has the ordinals as well. I can derive transfinite induction in this system, so the system is robust, and the theory is robust in a Florio-Winch-Krauss sense. Sorry, I have not shown that yet. Now I'll come to, this should be higher type, not upper. Higher type ordinal abstraction. So I've shown you so far that I can derive from finite induction, which is good. That's one of the things required for the system to be robust. I'll now show that I can also derive higher type ordinal abstraction. So I need some lemmas. And the first is that for any ordinal, that ordinal is identical to the property of being a well-ordering of individuals, think on a simple case, order isomorphic to the restriction of well-ordering of the ordinals to that ordinal. So think about deprivation, except that you only think of the ordinal of iterating the ordinals which are less than this particular O. So any ordinal is identical to this property. What this tells me is that the well-ordering of the ordinals and its restrictions are yardsticks. That's something that I need to prove, and that's super cool. Second lemma. No well-ordering of individuals is order isomorphic to the well-ordering of the ordinals. And how do I prove this? Burali-Forti style paradox. And now this is, I think, the main, or perhaps mathematically, the main thing I find intriguing and nice about it, and I didn't expect it, is that what before led to paradox now leads to a theorem. So that makes, I mean, of course, I mean, one can go different ways, but that makes me think this might be going in the right direction. I've learned this in the past. I think it's best not to go through the proof. We can talk about it later. But perhaps that's too much. But yeah, if you go through the proof, you'll see that basically the same kind of reasoning you had before will lead you to show that to get to the Burali-Forti paradox will show you this lemma. And I take this to be the positive lesson of the Burali-Forti paradox. It's teaching us something. And by appealing to lemma 4, I can show that for any well-ordering of individuals, there is indeed some ordinal O, such that R, the well-ordering of individuals, is order isomorphic to the restriction of the well-ordering of the ordinals to O. This is a yardstick, and so what this tells me is that this R, this relation between individuals, will fall under some ordinal. And so I derive from this higher type ordinal abstraction. Incidentally, I think that by being able to derive higher type ordinal abstraction, this reveals that the characterization of ordinals harmonizes with Frege's constraint. So this is something that's very important for the logicists, not just for Frege and Neo-Fregeans, but also for Russellians. So the idea roughly is the following. Canonical applications of mathematical entities to the characterization of the world must be contained within their nature. I mean, I would like to be grandiose and to say that you can be a logicist about all mathematical entities, but I can be grandiose, but I won't ever have a proof of that. But you can do it piecemeal and start to think about particular domains of mathematics and see whether you can characterize these mathematical entities in a way that makes sense of their application. And by characterizing ordinals as properties of well-orderings, that certainly delivers that, because it is within the nature of the entity to be typing the well-orderings in the way it is. So canonical applications of ordinals are to characterize well-orderings, and I've given you a characterization of ordinals that delivers just that in the best way possible. And I've shown now that it delivers a robust theory in Fourier-Milch-Krauss sense. And it's logical theory, if you think that modality is logical. And it does not solve Pareto metaphysical problem faced by the no-class theory. I ensured with my definitions that it wouldn't do that. Infinity. I said, so how is it? So for in which Krauss, they cannot derive that there are more than 2 or 3 ordinals, which is a pity. I can derive that there are infinitely many. That's so good, already good. And to prove this, I needed to appeal to the principle I told you before, planetary finitude, that the universe, though it might be necessarily finite, is such that for any finite cardinality, there could have been n many things, or a property such that it has exactly n many things. I can also show the existence of a number of limit cardinals, at least natural number many limit cardinals, which is also cool. And this won't be apparent from this talk, but I also have this project that's showing that set theory can be, that I can give a definition of set and that I can show that set theory is logical. And for that project, I need these many, I don't need these many ordinals, but I need a few limit ordinals. And this helps me in this project. Okay, so wrap it up. I've so far given you a characterization of ordinals, show that it's robust, and I've used this logic for doing that. So this is kind of asking for the pursuit of a Logicism project. So let me give you then very quickly some hint on what is the Logicism project that I've been developing. I've called it Upper Logicism, and it can be given as a template, depending on the particular field you're interested on. So it's a conjunction of following theses. The first idea is that for any entities that you're interested on, in particular for any theory of mathematics that you're interested on, its primitives should be characterizable using only logic. But they should be characterizable as higher type entities, as properties or relations of some sort, in the way that Russell thought that the numbers and so that the natural numbers and not only those were, but in particular having in mind the applications constraint, because that would be the best way of saying true to the applications constraint, to the Frege constraint. So there's a commitment, a robust commitment to higher orderism. So the idea that I'm using type theory and that the type restrictions make sense and they cannot be given away. So I cannot at the end say that, no, really what I have is first order quantification, and these types are to be dismissed. No, pure quantification and quantification to predicate position are legitimate, and they are not to be reducible to first order quantification. Planetary plenitude, I've already explained to you what this principle is. Just to, I'll anticipate a bit, but planetary plenitude is very important for me to be able to go beyond Russell and do what he didn't do. It was in virtue of planetary plenitude, so the biggest objection to Russell's project is that it cannot derive the infinity of the natural numbers. With planetary plenitude, I can. So that's how important it is. So it's part and parcel of my picture. Then there's a commitment to interpretability of a mathematical theory. If I have a mathematical theory, I'd better have a logical theory that can derive all its theorems. And it should be able to derive its theorems in the way that these theorems can all be seen to correspond to necessary truths, and respecting the translations that I've given of the primitives of the theory in higher order terms, in logical terms. But because we have Gödel's incompleteness theorem, we know that a Logicism program cannot just consist in deriving the theorems of a mathematical theory, because that will never give you all the truths. So how can you get to all the truths? So the idea is to show that once interpreted in the right way in higher order logic, any sentence of the theory, if true, is necessarily true, and if false, necessarily false. Because if the truths are necessarily true, they can formulate them all in purely logical terms that gives me at least one way into thinking that what I have is pure logic. Because one way of thinking about what sentences are logically true is to think that these are the metaphysically necessary truths which are formulated in pure modal, plural type-theoretic languages that are formulated just in terms of logic. And so this is what to be an upper logicist about a particular domain is. And as this just says that what I've told you before, that I've been able to do a bunch of these things for arithmetic. And for those interested, I've been able to do it using only the modal logic K, which is the weakest normal modal logic. And that's striking even to me. And just as with ordinals, natural numbers are typically ambiguous. They recur along the type-theoretic hierarchy. So let's now come to ordinals. This all comes because I think that now I have the seeds to start a defense of a probabilism about ordinals. I've shown that the notions of ordinal and the Western relation between them, presumably the primitives of a theory of ordinals, can be shown to be characterizable in pure higher modal logic. I've interpreted some results about ordinals, and so at least I've shown that the theory is robust. At least that, though this falls short of a full being able to interpret a full theory of ordinals. One of the reasons is that to anticipate, there's no canonical theory of ordinals that's not formulated in set theory. I mean, this is perhaps too much. Takeuchi has some theories, and actually one of my future goals is to see how much I can interpret of Takeuchi's theory. But besides Takeuchi and perhaps some lost papers, people don't even typically give a canonical theory of ordinals that's not seeped into set theory. Necessity of ordinals. I have not shown this, but I know that it can be shown because it just relates to the work I have on arithmetic, that any sentence of a theory that only has as primitives, then the property is an ordinal or the predicate is an ordinal, and the relation less than or equal to between ordinals. I know that once I interpret this once I interpret a theory couched in this language according to the definitions I've given, I can show that the sentences of that theory are, if true, necessarily true. And so this would circumvent a version of a global theorem, incompleteness theorem. Okay, so what has happened? I've given a higher type characterization of ordinals, which overcomes the metaphysical objection. I've given a robust and logical theory of ordinals, which seems to be capable of supporting a probabilism about ordinals. So future work. I've already mentioned this first point, that I want to formulate the canonical theory of ordinals, and I'll start by looking at the theory of ordinals of Takeuchi and see how much I can derive from that theory. Let me say that it is up for grabs whether one should be required to derive all that, for instance, Takeuchi derives, because it might be that Takeuchi's axiomatization is being driven by set theoretic results and not by the nature of ordinals. Then I would want to do the same thing for cardinals, and I think it won't be so easy. But that's one second step. And then I want to continue the development of this project. And there, I have some good news. The Portuguese Science Foundation has given me some money to work on this for 3 years. So I'll have a team working with me. And this is it.
So thanks a lot. We have time for questions, comments, discussion.
Yeah, like in order to make the questions, I think I will need to go unpacking them because there was a lot of stuff there, and I did not follow everything for sure. So one question about how you characterize the ordinals. So what happens with the well-ordering between ordinals?
Mm-hmm.
Like, it itself is like, in order, like what is that? That has an ordinal of a higher, like some yardstick somewhere, I don't know where, like up there in the
hierarchy, yes.
And then you keep playing the game, right?
Exactly.
So
yeah, that's the idea.
Since Burali-Forti paradox, like issues, like under these lenses, it's like they forgot about the types.
Exactly.
You just have to search for them.
Next type.
Above.
Exactly.
Like, some type farther away. Right?
That's precisely the idea.
I see.
So the Burali-Forti was just ensuring you that you could actually characterize the well ordering of the ordinals. It's just that you need to go higher on the types.
Search high. I see. And so then you transform what was the paradox for the lower type.
Yeah.
And as a result about the fact that there's no such well ordering
down here. Yeah.
That was cool.
Yeah.
As far as I could understand.
Yeah, that's it.
And so another question is, so what does this require? So something is a yardstick if and only if that's the first is strongly rigid, right?
Yes.
This entails it's necessarily existent.
If I have a serious actualism.
Yeah, serious actualism. Okay, and the rest of it says.
So that it necessarily exists.
Yeah.
And this says that there is possible to find some ordering.
Well ordered, it's isomorphic.
It's isomorphic to it.
And this is isomorphic to it. It's just this abbreviation for.
Yeah, the statement in a higher order logic. To bear in mind that it's an isomorphism that crosses types.
Yeah, that's what I was going to ask. Right?
Yes. But I can define all of that. I mean, those relations are all okay. So the isomorphism will be of.
That's not a relation that's typed, right?
Or it is. So the isomorphism will be a relation between things of this type and things of this type.
Of course. Yeah.
So, or type of ordinals, type of objects.
Yeah.
So these are there.
In that sense, it's cross-type.
Exactly.
Yeah. And things were already there.
Precisely.
Finding the relations.
Yeah.
Okay. I'm thinking.
Yeah, thank you very much. It's a while I didn't hear anything about ordinals in this class, so it was nice to hear you. Now, I'm probably going to, you're pointing to the moon and I'm going to ask about your finger, so excuse me.
Good.
I'm thinking about knives and handles and angels and their parts, right? So you put them like at the same metaphysical levels.
Right?
Well, it's striking to me that well, it's not the same, the knife handle and a knife, right? So ones are objects, the other ones are part of those objects.
Right, that's right.
So I don't know if they need a different in time, you know, to
Because
see
they're
what is going on.
Because they're
We're
parts.
talking about possible words, right? I mean, like with angels, even if they're necessarily existing, the wings maybe are not necessarily existing, or yes, I don't know. The sex may be a contingent, but the head, they probably need to be necessary parts of the identity of a certain angel, right? So I was caught by that in thinking that when you were talking about incompossible possible words.
Incompossible objects.
Oh,
I mean, the words are incompossible too, but in a related sense, if you want. Two words never obtain in the same word.
Yeah, exactly. Yeah, but that goes without saying, right? I mean,
Yes, but the objects are incompossible.
One word is an alternative to another one, right?
Yes.
Well, what's the idea? My question would be, what's your idea of possible words being there, and some of them being composable or not?
No. The incompossibility is between. No. It's between objects. So the idea is that H plus B is incompossible. I mean, if I could even say this, is incompossible with H plus B star. Because if I want to form H plus B star, I need to remove the blade from H plus B. And so I'll need to destroy it. I mean, this is just a motivating example. I don't really need to appeal to this story about what makes a blade and what makes a knife. It's just the idea that, look, for all we know, there might be. I mean, how is it so? Salmon had this example of perhaps one of his sperm had the egg from which he results could have been there could be a different sperm that united with it, and then what would arise would not be salmon but nomen, and so salmon and nomen would be incompossible. So I don't need this particular story about knives. It's just a motivating example to like get intuitions going without much fuss.
I think maybe I misheard incompossible word.
Or maybe I misspoke.
Hi, so thank you. Yeah, that was super cool, but I got lost at many parts of it. So maybe what I'm going to ask, is it like too long or too basic to answer? So just, you started talking about the so-called Hume principle, the number of asks, and then I saw Crispin Wright at the end of the references. So I was kind of thinking, there was this debate whether, that principle is like, with that principle we can say Logicism, we can say Frege, he didn't need the basic law 5.
That's right.
Right, and I was wondering, just kind of like to go back to mention it, and then I don't really know how we end up with that principle with your proposal. I mean, I guess you have no problem with it, or that's just what I want to ask.
I mean, so let me.
It's relevant, yeah.
It is very relevant because it's very relevant to see, in a sense, who are my ancestors. So think about the debate on Logicism. But as it's happening when Russell comes and says, Frege, look, there's something that's not quite right here. And then Frege looks at the result and you try some stuff that doesn't really work, and for him it was that. We know the Neo-Phrygian story, that's kind of the one that's like the closest to us, so we know the people that are descending from Frege. But Russell, I mean, he didn't stop there. He had the whole Principia. So Russell's thought was, look, where Frege went wrong was in thinking that numbers were objects. And I mean, everybody, even more nowadays, because we have the privilege of having some results and better understanding the mathematics. I mean, of course he needed to think that they are objects because that's what allows him to have this bootstrapping from which he can construct numbers out of nothing via Hume's principle. At the end, as we know, doesn't really need basic law 5. But by then, Russell looks at it, and I mean, I don't know if this was exactly the Russell's reaction, but certainly something along these lines, which is this assumption that numbers are objects seems wrong. Actually, there are letters from Frege, I'm now appealing to authorities, at the end of his life, wondering, perhaps I went wrong when I thought that numbers were objects, and what I should have said was that they are properties of properties or concepts of concepts, whatever thing you find as close synonym or almost synonym for that. And so Russell took that line. For Russell, the big problem and the reason why people were so dissatisfied was thinking, look, this is all well and good, but how can you say that mathematics is logic if you can't even derive the infinity of the numbers? Like, logic really is like, what's going on? And so actually there's there are other problems with Russell's system, but the consensus seems to be that, all the other problems like the types, there was a ramification of types, but you can do away with that. Later on he relies on some forms of choice, but he doesn't need that for arithmetic. So the big issue was that just he didn't have a system that's strong enough. And so that's, if you look at the end of the day, like inconsistency versus system that's not so strong, like perhaps the Russellian line is worth pursuing. That's what I've done. And I'm doing that across the board. So I've done that for arithmetic, and I'm thinking, look, I think this works, and let me see how far I can push it. canonical. I said ordinals are not sets. And in particular, they're not the sets that the set theorist identifies them with, because they just give you particular yardsticks. I mean, let's put it that way. So if the universe can be well ordered, the universe of sets, it should fall under some ordinal. But ordinal, that won't be a set.
Didn't you say something about being canonical, about ordinals?
There's no canonical theory of ordinals. So there's no theory that's formulated using only primitives that you'd expect from a theory of ordinals. All the theories we have, we get them via the primitive, via membership. And so, I mean, I exaggerated, as I mentioned later on. So Takayuti is the only person I know, probably there are more, but Takayuti is the authority I know who has some theory of ordinals. But as it happens, mathematicians have not, because they have set theory, that's like, we don't need to bother about that. They just import the definition of ordinal from set theory. But I find that striking. We don't do that with numbers.
I mean, you can also just, I mean, you have the definition which doesn't define the set, right? I mean, when you say that an ordinal is an equivalence class of well-ordered set to isomorphism, that's a sort of canonical system for ordinals, you know?
I mean, if I don't take it to be a class in a set theoretic sense. This might be the way. I mean, there's one way of understanding the type theory where you see that the meaning of type theory and of type expressions is given in set theory. That's why it's so important to me that I think higher order quantification is not reducible to set theoretic talk, because sets are all objects. Then I cannot talk about the well-ordering of the sets. I think I should be able to talk about the well-ordering of the sets, if the sets are well-ordered.
More questions? No one? So maybe we leave it here. Okay, thanks a lot.
Thank you.